Okay. So, it's just opened for last. So this is phase equilibrium and information on, I don't know what symposium this was. No, this is not the one I want to share with you guys. The one I want to share with you was a straightforward document. So I think it's this one. Straightforward document from the internet. It has some easy flow. Yeah. So this is the one that I want to share with you. So this one explains to us about phase equilibrium, the phase rules and degree of freedom. But I don't think, did you guys, when you are learning from class, look at the degrees of freedom of your molecule or not? Hello. Did you not do this part, degree of freedom, in your course?
Mudo has been tripping on chemistry lectures, so I have no idea.
All right. Anyway, let us look at what phase equilibrium is all about. So phase equilibrium is a study of the equilibrium which exists between or within different states of matter, namely solid, liquid, and gases. So the equilibrium that is going to exist when a molecule is changing in between these three states. I'll give you an example of fridge, in a fridge. Okay, so in a fridge, when you do not have a lot of things in the fridge, you're going to find that when you open your fridge, there is vapor that comes out. Have you ever witnessed that?
Yes.
Yes.
So actually what happens is this. We consider the fridge as a closed system. Since it is a closed system, what happens in a closed system is that when a solid is subliming, okay, so sublimation, when it is changing from a solid to a gas, gas condenses back to a solid. Okay, now these two processes, because initially you do not have a gas, so the rate of conversion of a solid to a gas is higher than that of a gas to a solid. But as the amount of gas is increasing in your closed system, the rate of conversion of the gas back to a solid also does what? Increases. And then a state is reached where the amount of solid that is converting into a gas and that of a gas getting back into a solid is equal. If you remember the definition of dynamic equilibrium, we said this is a state when the reverse reaction is equivalent to the forward reaction. So in this case, when a molecule is changing into a gas and the gas back into a solid, when they are at equal rates, that is an example of a phase equilibrium. So a solid, before I go there, let's come here. Phase, where a phase is defined. A phase is a region where intermolecular interactions is spatially uniform, or other words, physical and chemical properties of a system are the same throughout the region. So if you look at a solid will have the same physical properties as well as a chemical property. If you take water as a solid, it has the same, irrespective of which side of the solid you're going to be looking at. It will have the same properties, meaning these properties are what? Uniformly distributed. That's what a phase is. So if you look at a solid is a phase on its own. A liquid is a phase on its own. A gas is also a phase. That is why equilibrium, phase equilibrium is therefore when you are looking at the equilibrium when there is an interchange between phases, the equilibrium that is existing at that interface, at the exchange point, that is phase equilibrium. We all know the definition of equilibrium. We've been looking at this one for quite some time, but just to refresh, they're saying it is a stage when chemical potential of a component present in a system stays steady with time, meaning you cannot see any change. Whatever is happening forward is happening backwards, and hence everything looks even, irrespective of there being changes back and forth. We do not see any changes because the back and the forth changes are equal. So that is what this equilibrium is all about. So when you're looking at phase equilibrium, that's actually what we study. So within the same state, a component can exist in two different phases. You are in one state. Okay, so say you are in a solid state. When you are looking at just a solid state can exist in two different phases. When two different solids are combined to form one solid, they will be two different solids combined together. And since it is two different solids that are combining, we call these as two different phases, because one solid has its own properties and characteristics that are just respected to itself. And then on the other end, you have another solid that has its own independent properties. So should you mix two solids together, an example, salt and sugar. When you mix salt and sugar, these are two solids, but these solids each has its own properties. One of the very known property is that sugar is sweet, salt is salt. When you combine the two, each one of them has its own property. Therefore, we are going to call such a mixture as a two-phase mixture. Okay, so that is what actually a phase is. And here they are saying when you bring two immiscible liquids, they'll also coexist in two different phases, because these two liquids have different properties. Water and oil, for example. Water has its own properties, oil has its own properties. Should you mix the two, they will not combine. Instead, they'll be in two different layers, and each one of these will have its own characteristics depending on which side you are looking at. So that is a two-phased system. All right. Then this diagram here is actually just explaining the change in a phase. All right. So a liquid, when it is going to a gas, we call that as boiling. When a gas is getting down to a liquid, we call that as what? Condensation. So whatever energy is used to convert a liquid to a gas is the energy that a gas is going to give out to produce a liquid, as long as you keep the molarity or the number of moles, actually not even the molarity, but the number of moles constant. So if you vaporize 2 moles of the liquid, it will consume a certain energy. If you condense 2 moles of the same from a gas to a liquid, it will give out the same amount of energy as it acquired when it was vaporizing. When a gas is going into a solid, it's condensation, but when a solid is going into a gas, it's sublimation. Anyway, this table, I think you guys have looked at it from grade 8 or something. Since your syllabi has been changed over time, you people learn a lot of things earlier than the time we used to learn them. So I believe this particular part you should have come across this one twice in your secondary school study, irrespective of which science you were taking, it be general chemistry or whatever you call it. All right, so applications of phase equilibrium. They're telling us here where we can actually apply the concept and the knowledge of phase equilibrium. So one of the applications is in the production of different allotropes of carbon. You know what allotropes are? Hello?
No.
No, sir.
You don't know what allotropes are? Okay, you guys are not studying science, so that's a research for you. When we meet tomorrow, that's the question you will have to answer before we proceed. Find out what allotropes are. And then it is also applied in lowering of the freezing point of water by dissolving salts, which is a brine. This one here, you don't usually look at this application. But if I take you to very cold regions like Canada, these guys actually appreciate this particular part of application of a phase equilibrium. You know, in Canada, during winter and some other cold regions of like Russia, you find that roads, most of the times, especially in the night, the roads are going to be covered in ice. And then people in the mornings have to move and stuff for work and other stuff. So what actually happens is that early in the mornings, there are council people that are in charge of keeping the roads smart and stuff to apply salt on the ice. By the time people will start moving about, this ice would have melted to a liquid and the roads will be clear for use. So this is one of the applications of what? Phase equilibrium in terms of lowering of melting point, freezing point, all right? Then we have purification of components by distillation. Distillation, you guys have learned and have used probably this particular experiment once, and then usage of emissions in food production and pharmaceutical industries. So you can apply this particular concept there. And then you are saying solid liquid phase equilibria as a special place in metallurgy. And then melting point of alloys of copper and silver is lower than, so these are just applications. And then here is a phase diagram. This is a phase diagram of carbon dioxide. So this is an example of how a phase diagram looks like. Now, every time you come across a phase diagram, you should be in a position where you can interpret what is on a phase diagram. How clear is this diagram? Can you see it clearly on your side?
Yes.
Okay. So just to take a look at what this diagram has. So this diagram is divided into 3 sections. It has this blue section here, which is a solid, the yellow part, which is a liquid. Then we have this light green part, which is a vapor. And then we have this, is it orange or something here, which is a super fluid. Now, here, what you should understand is that there's this curved line. This curved line, it is representing a barrier or a point of change. This is a phase change line here. So this line is representing a change of a solid into a liquid. And this line you're seeing here from this point to this point is showing us the change from a liquid into a vapor, a gas. And then down here, you can see this line here is the change between a solid and a vapor. This point here, which is known as the triple point, is actually a point where you're going to find your solution or the molecule you are studying existing in all 3 states. this triple point. It's the point at which your molecule exists in 3 states. So at this particular point, this is the phase diagram for carbon dioxide. At this particular point, carbon dioxide is a solid. At the same time, you're going to find a liquid carbon dioxide here. At the same time, you're going to find a gaseous carbon dioxide at this particular point. The quantity with which these states are in is unknown, and you cannot tell to say, okay, amongst the 3 states, this is the one that is going to be in higher proportion than the others. You cannot, but at this state, you will be able to tell all 3 states are existing here. So this diagram actually can help you understand what happens when you lower the pressure, when you increase the temperature, when you reduce the temperature and you reduce the pressure, what is actually happening to your molecule of interest. This phase diagram you're seeing here can actually help you understand how you can extract oxygen from the air that we breathe. The process that they are doing right now in the creation of carbon dioxide that is being used in corona centers uses this same concept, all right? It's an expensive process to carry out because you need very high compressors that have to compress the gas to reduce the pressure, all right? So when you are reducing the pressure, look at what is happening. When you are reducing the pressure, the amount of temperature that is needed is actually also reducing to convert a gas into a liquid, all right? So if this was a phase diagram of oxygen, we reduce pressure and say we want the change to happen at room temperature. This time temperature is around 20 degrees, so say you want it to be happening at 25 degrees Celsius, yeah? So meaning at this particular point, if you were studying, you have to extrapolate a line down here up to there and then come to the pressure side and find what pressure is required. So say it is 60 bar. So since pressure is in bar here, you require 60 bar. If you require 60, so if you can reduce the environmental pressure, the outside pressure or the pressure within the system down to 60 bars and you keep the temperature at 25 degrees Celsius, you will be able to convert, if this diagram was for what, instead of carbon dioxide, oxygen, you will be able to change oxygen from a gaseous oxygen going into a liquid oxygen, okay? This is how you can extract it. So this is one way in which you apply this same concept. Questions can be asked. What temperature is for what purpose? That is on the triple point, all right? So I was explaining the triple point for you and I've just explained how you can use this phase diagram. Now, this phase diagram can also be used to find normal boiling and melting points of a given substance. So melting point, actually boiling point, is the point at which it's the temperature at which your pressure in a liquid goes to the pressure of the surrounding, all right? So most of the time we take the surrounding to be at 1 atmosphere, okay? So therefore, when you are at 1 atmosphere, what temperature makes the vapor pressure of your solution to be equals to 1 atmosphere? At that particular temperature, boiling begins, okay? So boiling always refers to atmospheric pressure. What temperature causes the vapor pressure of your solution to get to the pressure of the surrounding, which is 1 atmosphere. So if they give you a phase diagram like this one and they ask you to tell what the normal boiling point is, just go to 1 atmosphere. This is in bar. what is the conversion factor between a bar and an atmosphere. If you find what that is, you will be in a position where you can tell in bar which pressure, and then you extrapolate a line. When it hits this line, come down and get the temperature. So the temperature you get this side is the normal boiling point. Normal melting point, the same, all right? It is the temperature at which the vapor pressure of a solid gets equals to the atmospheric pressure. So if this is carbon dioxide, if that's what we were doing, so we assume this is the room, this is the pressure which is equivalent to 1 atmosphere. This line eating here, when you drop a line coming down, the temperature you find here is going to be your melting point. When we reach this particular point, we drop a line down, the temperature you get here is the boiling point of carbon dioxide. And then you have this point which is known as the critical point. The critical point is actually a point at which a solution cannot be condensed. Okay, this critical point is the point at which your gas cannot be compressed. You cannot condense it into a liquid. Okay, and that fluid or the gas that you get, the solution you get to get beyond the critical point is a superfluid. Okay, so when you go beyond the critical point, you get a supercritical fluid. So supercritical fluid is a fluid that cannot be compressed into a liquid. Okay, it just remains in that state there. That is what this particular point is. So every time a question is asked, the point beyond this line. So this, for carbon dioxide, the supercritical fluid, carbon dioxide has a supercritical fluid beyond, or becomes a supercritical beyond 30 degrees Celsius and a pressure above 80 bar. So above 80 bar going up there, and the temperature increasing beyond 30 degrees Celsius. You can see here, this region is what is going to be present. Carbon dioxide exists as a supercritical liquid, as a supercritical fluid in that particular region. So all in all, this is your phase diagram. So this diagram actually explains the changes that are happening to your system. Is there questions?
At the critical point, is it in liquid state or gaseous?
Okay, so at a critical point, you expect to have your liquid and your vapor. So your liquid and your gas state is going to be there. But beyond that point, it's neither a gas nor a liquid that you get to have. You get to have a supercritical fluid. So at this particular point, you have both the liquid and your gaseous state of your molecule. But beyond this state, your molecule just becomes a fluid. You can't define it as a gas, neither can you define it as a liquid. It has its own properties. That's why it has its own name, supercritical fluid. Any questions? So we are not going to go beyond this point, because going beyond this point actually now brings in these things that I don't think you guys should learn. This is not part of your course, because if I look at, I think I have a tutorial sheet that has some questions on phase equilibrium. And if I look at that particular tutorial sheet for you guys, I can't see, unfortunately, any question that has to do with any question that has to do with that part of chemistry. So, okay, so I'm looking at the questions right now, and that's not part. Okay, this is not part of your. This is not part. So what we're going to do right now is after. Okay, I think we don't need to wait. We have 4 minutes. I think we can answer these questions on the phase diagram, and then we shall call it a day for today. We'll continue tomorrow, where we will start looking at the, I think we start looking at the properties of solutions, and then also look at their colligative properties. So what I'm going to do right now is I stop sharing this one, and then I share a new screen, which is this one. Okay, so you guys are able to see the question that has come on the so tutorial sheet. This tutorial sheet is tutorial sheet 9, which I believe you guys have. So tutorial sheet 9, question 10 is on what we are just from learning. So now look at this particular question here. So they've given us a phase diagram of carbon dioxide, unfortunately. So this is a phase diagram of carbon dioxide. And this side is pressure. So whenever you have a phase diagram, it's going to have pressure on the y-axis and temperature on the x-axis. Now they are saying, assuming we live at sea level, 1 atmosphere, where the pressure is 1 atmosphere, how could carbon dioxide be liquefied? All right. So if you live here, where this is the pressure, 1 atmosphere, how could carbon dioxide be liquefied? Meaning, how will carbon dioxide be changed from this to a liquid in that state? So how will this change in the phase B? How will you get to that one? So if you can even check, 1 atmosphere is here. Okay. So if you do not change your pressure, if you keep your pressure like that, there is nothing that you can do that is going to change carbon dioxide into a liquid. All right. So the only way you are going to change carbon dioxide into a liquid is if you increase the pressure. All right. So by increasing the pressure, check out, when you start increasing the pressure and increasing the temperature, both at the same time, pressure is increasing going up, temperature is also increasing going this side, you will be able to change what? Carbon dioxide from a gas into a liquid phase, which is that one. Otherwise, if you keep this one constant, then there is nothing you can do. So here they're asking, assuming you live at sea level, 1 atmosphere, how could carbon dioxide be liquefied? By increasing the pressure and temperature at the same time, you'll be able to liquefy carbon dioxide. At what temperature and pressure does dry ice sublime? So they want you to give us the temperature and pressure at which carbon dioxide solid goes into a gaseous carbon dioxide. So if you check out, they've given us this here, 1 atmosphere, negative 78.5 degrees Celsius. At this particular pressure and temperature, solid carbon dioxide sublimes. So just get this, 1 atmosphere and negative 78.5 degrees Celsius as the temperature, carbon dioxide will what? Carbon dioxide will sublime. Question 3, above what temperature is it impossible to liquefy no matter what happens to the pressure?